So let's take a look at, pick up where we left off last week. All right, so we're talking solving, factoring or solving polynomial equations. So what are we going to do with this? On the first assignment, it's going to say factor completely. But just remember why we're doing that. As we talked about last week, we're doing that to solve an equation. So a more important problem that we're going to do eventually, and I can't tell you exactly what assignment it's going to be on, but I'm going to give you a series of problems like this that say solve or find the zeros of or solve this polynomial equation, right? How do we go about doing that? What's our thinking? And what we're going to end up developing too, over the course of the next few days, we're going to look at different types of problems each day. And by the end of that, we'll come back together and we'll kind of draft like maybe even a little document. It's going to be our strategy for solving these kinds of questions. And a lot of that document is going to say things like, if the polynomial or a factor that we're trying to break down has 2 terms, then we'll try this strategy. If it has 3 terms, we'll try this strategy. If it has 4 terms, we'll try this strategy. But regardless of how many terms it has, this one has 3, right? But regardless of how many terms it has, there's always going to be a step above those that says, try to do this first. What's that? Factor out the GCF, greatest common factor, right? So that's always going to be a great idea. So the first step is, what can we divide away from each term or undistribute? Let's start with the variable part too, right? The variable part is the easy part. What power of x could I undistribute from each term? X to the 1, right? Because that's the weakest of all the powers of x. So that's the only one that I can divide away from each term. Make sense? I can divide x cubed away from that term, but I couldn't divide it away conveniently from the other terms because they're not powerful enough, right? So we'll undistribute or factor out an x. What is that leaving us with?
X squared.
If we do that. Yeah, so think about this now. If I'm dividing away an x, is that changing any of the coefficients? No. All it's doing is doing what to each power? By how much? Lowering it by 1. Yeah. So this first term is just going to become a minus 5x squared. Second term is going to be a 15x. Good. And the last one is going to be 270. Right? Okay, so good. We got the x out. Now this is actually the harder part. Is there a number that divides into all those? 5. What's your clue? And a lot of the things that you learned in middle school are going to start to become more important again now. How do you know if a number is divisible by 5?
It's got a 0 or 5.
0 or 5. Ends in a 0 or 5. Good, right? So we can factor out a 5. And remember what we said earlier in the year, we always want to include with the GCF whatever the sign of the leading term is, right? So we're actually going to pull out a minus 5. So we're going to end up then with a minus 5. And we already had that x there, right? And then what am I left with now? So now I'm going to take each of these and I've got to divide everything on this row by negative 5. So the first one's just going to be, okay, what's 15 divided by negative 5? Okay, so we're going to get a negative 3, then that had an x. And then positive 270 divided by negative 5. What is it again? Well, what is it? How many times does 5 go into 27? 5, it'd be negative, right? So I get 5 with 2 left over, so it goes into 24. So negative 54. Okay? Who's close? Within an order of magnitude, within a factor of 10. All right. So then, what about now? So that was good, right? When we factored out a greatest common factor, what did we accomplish? Well, we took this cubic polynomial and we broke it into a product of something here that was really simple and a quadratic polynomial. A lot easier, right? This one, if it factors, what are we going to look for to see if this factors? We've done a ton of these, right? If this one breaks apart, what are we looking for?
Oh, divided by itself. Well, divided by 2 and...
So it's 6
right?
and 9.
Okay, so those are the what? What do we call those? The magic numbers, right? We want to find the magic numbers that are going to multiply. We know that that's an x and that's an x because that's x squared, right? Numbers that multiply to negative 54, and add to negative 3. Let's go back and review the sign game we used to play when we're doing this in Module 3. If the two magic numbers multiply to a negative, what's that tell us about their signs? Okay, negative and positive. And if they're going to add to the negative, then which one must have been bigger? The negative would have been,
So it's negative 9 and positive 6.
there you go. So negative 9 and positive 6. And then out front, we've got our negative 5x, right? So now we've got it broken apart all the way. Why is that useful? Well, that's useful because now all we have to do is find the zeros of each of those factors. So what's this one going to be?
Positive
9. What's that one going to be? Okay, and this is the easiest one of the bunch. Although the first few times you do this, it might look a little strange. But what's going to be the zero of this factor out front? Yeah, right? We're asking ourselves, when would negative 5x equal 0? Well, negative 5x equals 0 if I divide each side by negative 5. X equals 0 divided by, who cares? 0 divided by anything is what? 0. Right? And that's always going to be the case. If I factor out a greatest common factor that's a monomial like this, so it's only got one term, and it's got an x in it to any power, what's the solution always going to be that goes with that? The 0 that goes with it. X equals 0 every time, right? It's going to get boring. It's always the same, but it makes it easy, right? Okay, so that's what we talked about Friday. So moving on. Now the next step is a very easy one. The next step is, how do we deal with factors that have two terms? Really simple. When we deal with two-term factors, we're just going to see if they fit any of these four patterns. And if they don't, there's nothing we can do. Okay? But sometimes they do. So what are these patterns? Let's just look at these individually. One of them is a difference of two squares, which we already saw. We already saw that in 5.2. Do you remember when we looked at product patterns in 5.2 or in 6.2? Just earlier last week. We talked about the conjugate pattern, where we said if we have a plus b times a minus b, those are conjugates because the terms are the same, but the operation in the middle is plus in one case and minus in the other, right? Remember what the answer was to those? When we multiplied those out? If we multiplied conjugate factors together, we got squared minus b squared, right? So all we're doing here is just reversing that, right? So if we're trying to not multiply things together, but instead break it apart into factors, if it starts off as a difference of squares, something squared minus something else squared, the a and b just stand for the first something and the second something, right? So if I've got something squared minus something squared, then it's always going to factor using that pattern. A squared minus b squared breaks apart into a plus b times a minus b. And you can flip those around, it doesn't matter. Order makes no difference. Okay, so there's one. That's a simple one. We already kind of knew that one. Okay, the next one is the simplest, the sum of squares. If the pattern is something squared plus something else squared, call it a squared plus b squared, the answer is it doesn't factor. That's it. That's as far as you can go. Okay, so that one's done. Now these two are a little bit more complex, but I'm going to show you a way that makes them really easy to remember. So let's take these kind of at the same time. Let's start with the sum of cubes. So if we start with a cubed plus b cubed, and then right along with that, we'll do a difference of cubes. Difference means subtracting, sum means adding, right? Okay, in both cases, when these break apart, if we have these patterns, they're going to factor into a small factor times a big factor. Okay, and the terms in each factor are going to be the same. The only thing that's going to change are the signs we put in between them, the operations. So the small factor is always going to have an a and a b, and the big factor is going to have three terms. Out in front, there's going to be an a squared. In the middle, there's going to be an a times b, and at the right, at the end of it, there's going to be a b squared in both cases. Okay? All we have to do is just put the signs in. So here's how it works. Well, first of all, one of them is really simple. The last operation is always going to be plus. It's never going to change. It's always plus. So the first and second, the first one and the middle operations are the ones that are going to change, and it's really simple. all you do is you look at the operation that starts in the pattern. So if this is a sum of cubes, a cubed plus b cubed, then that tells you that the operation in the little factor is plus. So if it starts off as an a cubed minus b cubed, the little factor is a minus b. The next factor, the middle one, is always just going to be the opposite of that. So if it starts plus, the second one's minus. If it starts minus, the second one is plus. That's it. Okay? So there's those two that are kind of harder. And then difference of squares, a squared minus b squared is a plus b times a minus b. Sum of squares doesn't factor, stays the same. Okay, turn to a fresh page where you can't see those and try them. Fill those in. Yeah. Fill in those blanks. Where's your map? Where's your notebook? Yeah, pencil. Yeah. Okay, what do we got here? Let's see, a squared minus b squared, difference of squares. Justine, how's that one go? That's going to be the product of what two factors? A squared minus b squared. A, good, a plus b times a minus b. That's it. Good, that's it. Okay, a squared plus b squared. How about that one? That's the, doesn't change. That's the one that doesn't factor. So that one just ends up being a squared plus b squared. It doesn't factor. Right? Can't go any further with that one. Okay, here's the two kind of tricky ones. So what about this one, Gage? What is a cubed minus b cubed? So a difference of cubes. Remember, that's the one where you have a small factor and a big factor. So how's that one go? Start a minus b. Good. Plus. Remember, there's 3 in this one, though, right? AB. And then the last one's always a plus. B squared. There you go. Good. Sum of cubes. Sum of cubes. What do you think, Mallory? How about that one? Good. Good. Right, remember, this one is going to match that guy, but then the next one's going to be minus. Good. And then plus b squared. Very good. Okay, we got them. All right, maybe we do. Try it again. Quick. See how fast you can write it down.
Did we just do that?
We did. A little more practice. This is one of those rare things that really helps to just memorize. You use them so much. right, first one. Caitlin. Sum of squares. A squared plus B squared. Number- That's the tricky one. I mean, it's kind of doesn't change. There you go. A squared plus B squared stays the same. Alexis, how about a sum of cubes? So just, well, so A cubed plus B cubed equals A plus B. You got the plus part, right? Times A squared. Good. Good. Very good. Okay, difference of cubes. Let's see, Gage, have you done one? No, you haven't done one yet. Did you do it? I picked on you already. Okay. Justin.
A minus B. And A squared plus AB plus B squared.
Very good. Last one's always plus. And then finally, A squared minus B squared. Ariel, how about that one?
A plus B times A minus B.
Very good. Okay, we got it. Okay, we're about out of time. I kind of talked too long. Tomorrow, we'll actually use these. And you'll see, this is pretty easy. That's the hardest part, is just knowing those. If you know those, using them is no big deal, okay? All right, keep cranking away on those assignments. Actual period. No, and I don't want to. Because it's this.
Just a word.
So you said you coded. What kind of code do you use for that stuff?
I'll show you.
Is it like Java or like C#?
It's actually a derivative of, it's a proprietary code that's just used